Hi, class. I want to talk about Project 2, and we're in a unit on probability and probability distributions. And Project 2 is just an activity to help understand the differences in probabilities between a theoretical probability approach to statistics or an empirical probability approach to probability, and there is a very distinct difference, and it's a very important concept. So, what we have to do here is generate some random numbers first, and you'll see here on part one, we're calling it empirical probabilities. And empirical probabilities are probabilities generated from data collection. So we're trying to be non-theoretical, and we want to see if we can come up with very similar answers as those that we would get if we were using all theoretical probabilities. And so think of it as like if you were in algebra, if you remember back to solving quadratic equations. And when you would solve quadratics, there were different methods that you could use to come up with the same answers in particular cases. So if you had a quadratic in standard form, you could factor it. And if you remember back to that like FOIL thing, when you would try to work with these binomials, and we would come up with factors. So, and then we would solve the equation. But then also, you can solve quadratic equations with the quadratic formula. So you had two different methods. You could solve a lot of times the same exact equation and come up with the solutions. And the difference here is we are going to do the same thing in a sense as we're going to solve the same questions for the most part, just two different ways and then compare them. And the only difference with probability is that it is going to not come up exactly the same, but very, very close. And that's one of the big differences between algebra and statistics. You know, we refer to the algebra as deterministic modeling, and probability, in statistics is probabilistic modeling, because there's a little bit of error involved there when you're trying to relate information from a sample back to the population. So we understand that, and so what we're going to do then is we're going to solve um, some problems here, some basic probability problems uh, with empirical approach, which is based off of collecting data. And see, we have the data here as a set of data values, and we're going to try to generate answers based off of this data collection. And then in the second part, part two, the theoretical probabilities, we're going to answer those same questions and a few more um, based off of the theoretical sample space that would exist. And then what we're going to find out is that, hey, are those answers close? And yes, now, are they very close? We'll see what we come up with. And again, this is just a helpful video, so I'm not going to tell you all the answers, but I'm going to just talk about how you can go through and get those answers. And again, now normally when we do the project, every student will generate their own set of numbers. And I have the directions here again. Students would generate 100 integer values, so these are positive numbers from 1 to 26 inclusive. So any number, any counting number in a sense from 1 to 26, uh, you'll come up with when we come over here and hit this button in the calculator. So that's just for part one. This table again is only for this first part. Now, to generate these numbers, I want to show you anyways, even though I already generated them, just so you know how to do that. Um, now, it's very simple. You go to Stat on the calculator, or Math, I'm sorry, go to Math. And under Math, you have, let's see, numbers and complex and probabilities and fractions. So but we're going into probability. I'm going to use my right arrow, go over to probability. And then you can generate random numbers, just all kind of random numbers with no restrictions on those. This is permutations, combinations, factorial, and then down here to number 5. We're going to generate random integer values. We wanted numbers from 1 to 26 to show up. So we go into random integer, hit enter, and now I'm going to clear that. Now normally there wouldn't be anything here. And you type in what you want to start. I'm going to start at 1. And then again, normally when you go in, there's like nothing here. And then you put in your upper limit, which is 26 for us. Okay, again, so 1 to 26, which is what we were supposed to generate here. N is 100. Now, I could type in 100 here, but I'm going to skip past that. We're going to do them one at a time. It'll be easier to keep track. And then I'm going to hit paste. So what this does here is some of the older calculators don't have this step, but you can just go right past that and not worry about if you don't have these steps right here, because as we go in and paste, then the older calculators just started like this, random integer, and you would put in the 1, comma 26 right here and get the same exact thing. So the comma key is right above the number 7 key. So here's your comma key down here on the right, or down here, right above the number 7 key. So you could type in 1, comma 26, parentheses, and now we're all at the same place in the calculator. As I hit enter, it just randomly generated me a number. So I got the number 4 showed up, and see here, it was 3. Every time you go in and you do this, you're going to get different numbers. And that's why I set up here the randomly generated numbers produce different values for each student. So as you're going through, if you're generating your own, again, you wouldn't expect them because again, they are random. And then I'll hit. So if I had a clean table here, no numbers, I would type in 4 here, hit enter again. Oh, 4 showed up again. I would put it right there to the right. That's doesn't usually happen. Okay, 21 would go here next. We enter. It says in here, I have randomly generated the 100 numbers between 1 and 26 and listed them in table from left to right. So this is what I mean from left to right. I started here, top row, and I typed them in first, the numbers I got, and then I went down to the next row and typed them in from left to right, just like I was reading down through a paragraph. That's how I put my numbers in there. And I hit enter again. So 4, 4, 21, 12. This would be 4, 4, 21 would go here, 12 would go here, and so on. 16, and you just keep, until you filled your entire table up, you would just keep hitting enter and putting the numbers in, and you would generate 100 randomly, right, generated numbers. And so again, for this semester, we have all students are going to use this same set of numbers, okay? So you don't have to generate them. I wanted to show you again how to do that because we are going to generate some stuff a little bit later in the course if we have time on some other projects. But for now, let's just use these numbers here and answer the question. So I'm going to take off my calculator. Okay. and look at these questions. So remember, we are empirical probabilities, which mean, right, okay, we're going to use these 100 numbers, empiricals based off of data collection. Do not use probability formulas for this first part, okay? So this is a statistics approach to calculating probabilities. And so how would we find, what would be the probability of getting the number 21 in one selection, okay? And we're thinking about our population. We're using this sample to generate a general um, idea of a population. But this is all we got, right? When you go out and collect data and you collect a sample, that's all you have is the sample, and then you try to infer to the population. All right, so getting the number 21 in one selection, how would I figure that out by having all these numbers up here? Well, I would look at how often 21 occurred in this set of 100 numbers. And then that would be my best guess at how it would look in the population. So I need to count up all the number 21s. And as we go through here and I go through to count them, there's one there, right? There's 21 right there. So that's one. And here's 21. There's two. And as I go through, and there's 21 there. So I have one, right? I have one here, I have one here, one here. That's it. Out of these 100 numbers, I have 3 21s. So my probability would be 3 divided by 21. Okay, 3 divided by 21. Or 100. Yeah, 100. It's 100 numbers, not 21 numbers. Okay, again. So let me state that once again. My probability for number 1 here is 3 divided by 100, or 0.03. It says write your numeric answers in decimal form. So we would take your calculator, three divided by 100, 0.03. So I would put 0.03 here for my answer. Now let's look at the next one. Okay, what's the probability of not getting the number 21 in one selection out of here? So if I randomly just went through and picked a value, what would be the odds that it's not a 21? Like if I randomly just picked this cell right here. Is it a 21? No. Okay. Is this one over here a 21? No. That's another selection. If I randomly selected this one cell here, is that a 21? No. Well, how likely is that? Well, if there's only 3 21s out of 100, that means there's 97 other numbers that are not 21. So my probability then would be 97 divided by 100, right? Enter. So you'd put that answer there, 0.97, so on. So you have to go through then and answer these based off of that same kind of thinking. You know, what's the odds of getting a 7 or a 10? Well, you got to go through and count up all the 7s and 10s. See, there's like one there, there's there. You got to go through, count up all the 7s and 10s, count up how many you get, divided by 100. Getting a number 5 and 15 in 2 consecutive selections, meaning getting 5 and 15 right beside each other in here. So like, see, here's 5, but it's not right beside a 15, so that doesn't count. Here's a 5, It's not right before a 15 now. So you have to look through here and see, do you have a 5 anywhere and then a 15 right after it? Now here's a 15, but there's no 5 and 15 right there. 1 and 2 right next to each other, right? They are not. So here's a 5 and here's a 15, but they are not right next to, they're not consecutive. Consecutive in regards to the table means that they're right beside each other, looking from left to right. Okay. Getting an even number or a number greater than 20. So you got to count up, there's a lot of those, right? You got to count up every number that's either even or greater than 20. Is this number even or greater than 20? No. Is this even or greater? Yes. Is this one even or greater than 20? No. Right? So you got to go through the whole table. Is this even or greater than 20? Yes. Is this even or greater than 20? No. You got to go through and count. 1, 2, 3. Here's 4, 5, 6, right? 7. And then you go through and you got to count. And as soon as you count through them, that's it. That's how many out of 100. All right, now getting the numbers 3, 25, 11, 17, and 9 in that order. You got it. The question is, do I have all of these right in a row? 3, 25, 11, 17, and 9, all right in a row, anywhere in there. Sounds like there's 3. No, 11. No, that doesn't work. 3, 25. No, I need a 3 and a 25, and I need all the. So, okay. It might not happen. Getting these numbers in any order in 5 consecutive. So you could have 11, 3, 17, 9, 25. Is that up here? 11, 17, no, 11, 17. And then you got to look. I don't have them in a row looking from left to right. So again, that might be the tough one to find. But all right, so that's part 1. And that shouldn't take you that long. And again, we weren't writing anything down, right? We did use the calculator to divide out, to put the answers in decimal form here. Let's look at the second part. So theoretically speaking, if we believed that we had true random numbers, they were represented perfectly, and so theoretically, what would be the answers if in our data set, when we collected it, they are all like perfectly evenly divided out between 1 and 26. And that's what I'm showing here. I got the numbers 1 through 26 all written out. Now I'm calling it a sample space. This is not what I got when I did my calculator random number generator. This is not what came up. It would never come up like this. But theoretically speaking, what we're saying is that every one of these numbers are equally likely to occur. Okay. So if you have a true random number generator, they would be equally likely to occur. And this, we could do some theoretical computations here. Now, getting the number 21 in one selection. Okay, getting the number 21 in one selection. Well, there's 26 numbers up here. There's one of them is a 21. So if I randomly went in here and just picked one of these numbers, what would be the odds that I happen to pick a 21? Well, there's one of them out of the 26 numbers that are up there. That's 1 divided by 26. And I got 0.0384, we'll say like 0.038 is close enough. Remember when we did the first part, now this is saying the answer is 0.038. And then when we did this part, we came up with 0.03. So very, very close. This set of random numbers, this sample of 100 numbers, approximated that probability for me, that theoretical probability, very, very closely. What we're finding out and what we're trying to justify with this activity, so that in your mind you understand that we can go out and collect samples and get very, very accurate answers to a lot of problems. But the key is randomly generated, right? We have to randomly generate. So we're able to show that with a true computer random number generator when we generated these numbers. And as you go through all these problems, you're going to find out basically the same thing, huh? Pretty darn close. And I added some more questions in here because these were questions that you should be able to answer from the chapter. Now, when you say getting the number 21 in one selection, is this a simple or compound event? So you have to decide that. Is it simple or compound? And if you look at my videos, then I talk about this. Okay, now number 10, not getting the number 21. And I talked about that up here. How, what do we mean not getting 21? Well, that's all the numbers that are not 21 up here. There's 26 numbers. 25 of them are not 21, okay? And what's that called, right? There's a term for that. When we say not getting something, you should be able to figure out what that is. Again, getting the number 7 or the number 10. We solved that up here, right? Solve that up here. And then there's a rule here. And again, this says getting the number 7 or, remember, or clues us into a certain type of theoretical, right, probability formula. And you have to decide, is it simple or is this a compound event? When you're talking about more than one thing, what probability rule is needed to calculate? We talked about rules like the addition rule, the multiplication rule, things like that, independent, dependent. So you got to figure that out. Getting the numbers 5 and then the number 15. And again, that's 2. We did that up here. Talked about that, right? 5 and then 15. That means 2 in a row. 2 right beside each other. How would you do that with a formula? Again, we talked about addition rule, multiplication rule, what this and means, and so on. So what probability rule is needed for this one? Are they independent or dependent? When we were generating these numbers here, were we generating them independently or dependently? We were using our calculator, right? So remember, we're using a calculator. So you have to remember that. Getting an even or number greater, we solved that up there. And then I added a couple in here. Getting these numbers in that order in 5 consecutive selections. Okay, there they are. And then this one in any order. So they are all the same problems. Just adding in some questions about the rules and the procedures. And then at the end here, you just have to answer this question. And so the whole idea is, this is what we were leading up to. This is a very important thing in statistics. Okay, so again, that should really help you get going and get through Project 2. And remember that Project 2, right, is graded. Traditionally, it's normally graded, and you have to just always check your syllabus and the announcements on when it's due and on the grading and points and so on, and the submission process. Okay, good luck with the project.